Good day everyone. So for today's video, we will be learning about the parametric equation. Parametric equations are a powerful tool in calculus that allow us to describe curves and surfaces in a more flexible and insightful way than a traditional Cartesian coordinates. This introduction will delve into the history of parametric equations, explore their significance in mathematics and beyond, and illustrate their practical application in our daily lives. So parametric equations are not just a different way to represent curves. They offer unique advantages when it comes to applying calculus techniques. And also, parametric equations can represent a wider variety of curves and surfaces, including those that are difficult or impossible to express using a single equation in Cartesian coordinates. This refers that the ability of parametric equations to represent curves that are not functions in standard Cartesian coordinates. They offer a more flexible and adaptable way to describe shapes. And parametric equations provide a deeper understanding of curves and surfaces. They can reveal properties and relationships not easily seen using Cartesian coordinates. This is the familiar system where points are defined by their x and y coordinates. Parametric equations expand on this system, providing a versatile approach. And also, parametric equation has a historical development of parametric equations, tracing their roots and evolutions. And also, parametric equations suggest that parametric are important not only in mathematics but also in various scientific and practical applications. It has a range of real-world applications of parametric equations demonstrating their relevance beyond theoretical mathematics. So now, let us talk about the history of parametric equation. While the term parametric equation wasn't formally coined until the early 20th century, the underlying concept has roots in ancient Greek geometry and the study of motion. Early mathematicians used geometric methods to describe curves, often relying on relationship between points and lines. The development of calculus in the 17th century, particularly the work of Isaac Newton and Gottfried Wilhelm Leibniz, provided a more rigorous framework for studying curves. However, these early methods were primarily focused on expressing curves as functions of a single variable. Example is the y is equals to the function of x. Although the term parametric equation wasn't formally coined until the 20th century, the underlying concept of describing curves using relationship between points and lines is existed in ancient Greek geometry. And also, um, based on the paragraph, the early mathematicians relied on the geometric methods to describe the curves, using tools like lines, circles, and conic sections. This approach was largely intuitive and visual. The development of calculus in the 17th century, pioneered by Newton and Leibniz, provided a more rigorous and systematic framework for the studying curves. And also, early calculus focused on expressing curves as a function of variable, like what I said earlier. This approach was powerful for describing many curves but had limitations for representing more complex shapes. So, the limitations of single variable function in describing curves that could not be easily expressed as a relationship between x and y. So this paved the way for development of parametric equations. The need for a more general approach arose when mathematicians encountered curves that could not be easily represented by a single function. For example, a circle cannot be described by a single function y is equals to the function of x because it fails the vertical line test. So we all know that. And this limitation led to the development of parametric equations, where the coordinates of a point on a curve are expressed as functions of a third variable, often denoted by the letter t, small letter t. This third variable known as a parameter. So that's what you call the third variable code is parameter. It acts as an independent variable that controls the position of the point on the curve as it changes. So based on the history of the parametric equation, there are a need of more general approach because the traditional function of y is equals to the function of x couldn't represent all curves. For example of that, the circle. So a circle is a simple example of a curve that cannot be described by a single function. This is because it fails the vertical line test. So meaning that a vertical line can intersect the circle at more than one point. So they make a solution. So the solution of it is the parametric equation. So parametric equation were developed to overcome this limitation. They offered a more flexible way to represent the curves. So in parametric equation, the coordinates of a point on the curve are expressed as function of a third variable, often denoted by letter t. So if you will see or notice in parametric equation, there will be using always or sometimes the small letter t as a third variable. So this third variable or the small letter t is called a parameter. So what is the purpose of this third parameter? So this third variable rather, sorry, the parameter t or it acts as an independent variable that controls the position of the point on the curve as it changes as t varies the point moves along the curve, tracing out its path. So uh, it, it it explains that the limitations of traditional functions in representing complex curves led to the development of parametric equations. So that's why we have now the parametric equation. So that's why the parametric equation came from, or um, parametric equation is a solution to the problem about the representing complex curves. So the introduction also of a parameter t, it allows for more flexible and dynamic way to describe curves, overcoming the limitations of single variable functions. So after knowing the introduction about parametric equation, what is parametric equations, the history of parametric equations, where it came from, how did it came from, how where did it came from. Let us now know why we need to study or why study parametric equation. Okay. So of course, there are importance on why we need to study parametric equations because parametric equations offer a several advantages over traditional Cartesian equations like what on the history said, but making them essential for understanding and applying calculus concepts. So what are those concepts? Number one, flexibility. Parametric equations can describe a wider range of curves. Also, it includes those that cannot be represented by a single function in Cartesian coordinates. So this includes circles, ellipses, and even more complex shapes. So that's why parametric equations is flexible. Also, number two, the concept of motion representation. So what is that? Parametric equations are particularly useful for representing motion, as the parameter t or the third variable can represent time. This allows us to describe the trajectory, velocity, and acceleration of objects in a dynamic way. So also t represents time. And next, the third concept, why we need to study calculus. Why we need to study parametric equation, because it has a ease of different differentiation and integration. Sorry, integration. Converting equations to parametric form can simplify differentiation and integration. So, particularly, of course, for the complex curves. This is because the derivatives and integrals of parametric equations can be calculated directly with respect to the parameter t, or the parameter that we call third variable. And lastly, of course, it has a geometric insights. We need to study parametric equations because it has geometric insights. Parametric equations provide valuable geometric insights into the properties of curves, such as their curvature, arc length, and also the tangent lines. So that's why we need, or it is the importance of studying parametric equations.
So today, um, let us now move on for the derivatives of parametric equation. So parametric equation, we represent the curve. So using the x and y, and also it represents the third variable, which is the t, and um or also for represents the time, because for example in projectile motion, example when we throw a ball here, um when the ball comes at this point, the velocity will be equals to 0. So to get the value of the velocity, we use the third variable t to get the velocity of the ball. So that's how parametric equation works. And now to get the derivative of parametric equation, we get the dx over dt of the function t, and also the dy over dt of the function g, or the third variable. And the formula is derivative of dy over dx is equal to dy over dt over dx and over dt. That is the formula for getting the slope or the first derivative. To get the concave, we use the second derivative. So to get the second derivative is we find the derivative of dy over dx. So example, find the slope and the concavity of the given parametric equations. So number one, we solve this. Okay, number one, x is equal to t squared plus 1 and y is equal to 2t minus 1 and t is equals to 3. So the first thing we do is get the derivative of dx over dt. So the derivative of x is the derivative of t squared plus 1 is 2t. And next is get the derivative of y, which is the 2t minus 1 is 2. So we have now the dx over dt and the dy over dt. Next thing we do is the formula for getting the slope. This dy derivative of slope is dy over dt over dx over dt. So our dy over dt, which is 2, so substitute, and dx over dt, which is 2t. So 2 over 2t. So to simplify, cross out 2. So mahibilin also t will remain. So and the final answer will be derivative is 1 over t. So we substitute the t here to get the slope. So the slope is 1 over 3. So that is our first answer. Now next, let us move on now to the second derivative, which is the concavity. Okay, next we do is the formula for the second derivative. So d squared y, or the second derivative, is equals to derivatives of dy over dx over dx over dt. So our dy over dx is this 1 over 3. So the derivative of 1 over 3 is negative 1 over t squared, and our dx over dt is over here, which is the 2t. So bring down 2t over 2t. Next we do is simplify. So 2t times t squared will be 1 negative 1 over 2t cubed. 2t cubed. Then now to get the concavity or the second derivative, we'll be substitute the t as this, the 3. Okay, so will be now negative 1 over 2 times 3 cubed. So the concave will be, or the second derivative will be, negative 1 over 54. So it is negative, so the concave will be downwards. So that's how you get the slope and concave downward. Okay, let us now next move on to the next problem. So the next given is x is equals to t squared minus 1 and y is equals to e raised to 2t, and t is equals to 0.944t. So to get the slope and the concavity, so first we need to get the slope. So first thing we do is get the derivative of x. So dx over dt, so t squared minus 1, derivative of it is t2. So that is the dx over dt. Next is y is equals to e raised to 2t. So derivative of it is 2 2e raised to 2t. So we have now the dx over dt and dy over dt. So for the formula for the slope, we'll be using the derivative of it. So getting derivative is equals to dy over dt over dx over dt. So our dy over dt is 2e raised to 2t over our dx over dt, which is the 2t, so 2t. And to simplify it, we cancel the 2, so we will be having now the e raised to 2t over t. So now we substitute the third variable or the t with 0.944t. So e raised to 2 times 0.9443 over 0.9443, we'll be getting the answer of slope is equals to 7. So next is getting the concavity. We'll be using the formula of d squared for the second derivative. So for the second derivative, we'll be getting the derivative of dy over dx over dx over dt. So, dy over dt. So, for getting the derivative of dy over dt, we'll be using the quotient rule. So, quotient rule, yes. So, t times 2 raised to the power of 2t, it's 2t guys, 2t minus e to the raised to the 2t times 1 and over t squared. So simplifying it, we'll be having the 2t e raised to the power of 2t minus e 2t e to the raised to the 2t over t squared. So that will be our derivative of dy over dt. So we have now the dy over dt. We will now put it in the formula. So our formula will be derivative of dy over dt over dx over dt. So our dy over dt will be e raised to the 2t times 2t minus 1 over t squared. So over our dx over dt is 2t. And we'll be having, and to simplify it, this 2t will multiply to t squared, we'll be having equals e squared e raised to the power of 2t times 2t minus 1 over 2t cubed. So to get the concave or concavity, we'll be substitute the value of t. So the value of t will be 0.9443. So e raised to 2 times 0.9443 times 2 times 0.9443 minus 1 over 2 times 0.9443 cubed, we'll be getting the answer of positive 3.44. So it is positive, so the concave will be directing to upwards. So that's how you get the slope and concavity of parametric equation.